This is a graph theory question. We have been given G, which is a connected, undirected, and weighted graph. And for this graph G, we need to determine which of these two statements is or are true. First one is saying that there exists a minimum weight edge in G, which is present in every minimum spanning tree of G. So now, what do we mean by the minimum spanning tree? For a given graph, it is an connected, undirected, weighted graph. So it can be something like this. It can be fully connected graph. There can be ways to reach from each node to every other node. So if we convert a graph into an MST, then what happens is that we make that graph minimally connected, which means there will be a path to go from one node to every other node, but there would be only n-1 edges for n nodes in such a way that the total weight combined of that tree would be minimum. Let us say the edge weights here is like 1, 2, 3, 1, 4, 3, something like this. So if we convert this particular graph into an MST, how would it be like? These are the 4 nodes at their place. We can have 2 different algorithms for achieving this, either Kruskal's or Prim's. And using either of these algos, we will get the MST for this particular graph as this will be edge from A to B, from A to D, and then now we cannot have the edge B to D because that would create a cycle. So we can go for either A to C or B to C. There are 2 choices. Either we can do this or we can have this edge. So those are the 2 MSTs possible for this particular graph. So what they are saying is there exists a minimum weight edge in G, which is present in every MST of G. So in this graph, there are 2 minimum weight edges, AB and AD. They have not mentioned that there are unique or there are distinct edge weights. They are just talking about the minimum weight edge. So there can be any number of them. We can have entire graph with minimum edge weights. For this graph, not all of its edges will be included in MST. We will only have any 3 of these 4. It can be like this or like this or like this. So it is not necessary that all of the minimum weight edges will be included in the MST. It may or may not be true depending upon if that edge weight is distinct or not. Here they have not mentioned if it is distinct. So we will say that the statement is incorrect. Now going to the statement 2, if every edge in G has distinct weight. Now here they are explicitly mentioning that G is having distinct edge weights. Then G will have a unique MST. Now if it is having all the distinct weights, let us say in this graph itself, if we change these edge weights into 1, 2, 3 and 4. Now in this graph, if we try to convert it into MST, what would we be doing? We will be going in the ascending order of the edge weights. We will be first including the one with minimum edge weight, then the next, then next. So this is the MST we will be reaching out to. So if there are distinct edge weights, then there will only be single unique MST possible for that graph. There is no ambiguity in that case. So yes, we will say that the statement 2 holds true, but statement 1 doesn't. So we'll be going with option A, saying that S1 is false and S2 is true. So the correct option is A.